Hi everyone, and welcome to this video on an introduction to what a structural vector autoregression is. A structural vector autoregression, as we sort of alluded to, it's a very flexible tool, especially for the analysis of policy actions on the real economy. So we discussed what a vector autoregression is, and we said that it was essentially a very flexible multivariate time series model in which we could have multiple variables, and we regress each variable against its past lags as well as the past lags of other variables. And it's unique in a sense that the assumption is that basically all the variables in the model are endogenous. Okay? Now, when we used a typical reduced form VAR and calculated the residuals as innovations, they led to one thing. But as we said, oftentimes we would want to use a VAR for structural analysis. And doing so requires the use of a structural VAR, right? So this structural VAR is a very flexible tool, especially for the analysis of policy actions on the real economy, okay? And the use of a normal unrestricted VAR can actually lead to misleading conclusions in many ways, which we'll try to give examples of in this video, right? And these misleading conclusions can be alleviated by using an SVAR. So if we use a typical unrestricted VAR, we could actually get misleading conclusions, especially if the data that we put inside is non-stationary. But generally, these are alleviated by using a standard SVAR, right? So for example, say you have this sort of policy question on inflation, right? So for example, the central bank in a country is anticipating a rise in inflation, right? So central bank thinks that inflation will go up in the next few quarters, right? And what they're going to do to curb this, of course, is it may raise its policy rate, right? If the policy rate increases, generally inflation is going to decline. However, okay, it so happens that after they increase the policy rate, inflation still rises as anticipated. Now, if you use a typical VAR or typical unrestricted VAR, you might wrongly conclude that the policy rate hike, that is the central bank increasing its policy rate, was the one that led to the increase in inflation, which is quite an erroneous statement to say, right? Because it's simply the central bank endogenously reacting to expected inflation, right? So if you ran an unrestricted VAR, it might tell you that story, but when you run a structural VAR, you know that because of this endogenous reaction to this expected inflation, this isn't the relationship that it should be pointing out, right? Another example, say fiscal targeting now. Suppose the government is anticipating a reduction in private demand caused by lockdowns during a global pandemic. Well, the government, okay, can in turn increase public spending. One way to increase, private demand, okay, or generally GDP is to increase, right? To increase public spending, right? And in doing so, okay, if they increase public spending, it so happens that output still goes down for some time. And again, if you run a normal unrestricted VAR, you might think that it's because of the public spending that the output declines, when in fact it's probably due to other reasons, right? So again, the fiscal policy or any policy in general reacted endogenously to expected outcomes, in this case, output for the fiscal case. And this is not the way of measuring the effects of public spending on the economy. Right? So we need a more sophisticated way that can account for these endogenous reactions to changes in the economy. And the key thing here is about isolating the impact, right? We cannot measure the impact of monetary or fiscal policy when the policy variable is reacting to movements of the other variable, in such a way that we need to try to silence out the noise and just focus on the relationship between two specific variables, right? So in order to measure the effects of policy, what we really want to do is to identify and isolate purely exogenous or purely independent movements or shocks, right? So these are the things we need to get shocks, right, to the variable of interest and see how the economy reacts to them. Right? This is referred to as the notion of impulse responses, right? What matters is that the philosophy underlying the SVAR is that we want to trace out the dynamic effects of shocks across the economy, and we want a definitive identification process to isolate out the shocks to see their real economic effects, right? So that's one aspect that we want to uncover, right? So how do we identify a structural VAR? Well, at the process of uncovering the structural model, the process underlying how we identify is first called identification. And what we do here is we want to identify totally exogenous shocks to the monetary policy rate and to fiscal spending. So we want to come up with shocks in such a way that these shocks are exogenous, okay? And these shocks sort of correspond to rising monetary policy rates or rise in fiscal spending, right? Or the converse scenario. So in essence, okay, identifying an SVAR is about isolating purely exogenous shocks. And what you do is you get the responses of the endogenous variables in your system, i.e. the variables in your system, with if it is hit by these shocks. So that's the goal that we're gonna have, right? So how do we do that? Well, okay. The author and proponent of the VAR, Christopher Sims, had this to say on identification. Okay. Identification is the interpretation of historically observed variation in the data in a way that it allows the variation to be taken or to be used to predict the consequences of the action not yet undertaken. It's quite a mouthful, but what we just sort of mean is after we identify these so-called structural shocks, okay, and the responses are captured, we could make predictions reasonably about the economic variables without needing to worry about the endogenous reaction problem that we had encountered if you use an unrestricted VAR. And to do this, we start by getting what we call the structural model. And the structural model looks something like this. Okay, so the structural model will isolate structural shocks and allows us to trace out the dynamics of the variables in the VAR, right? So how does the structural model look like? We need to first form a matrix, which I'll denote as matrix A, right? This matrix A, and it is a matrix of contemporaneous correlations, which is a matrix, right? It's some structural matrix, okay? And to be able to derive, okay, or obtain this particular matrix, the general strategy is to restrict that matrix with economic intuition to be able to recover the structural shocks. So what do we mean by this? We need to build matrix A in such a way that, okay, this matrix sort of corresponds to some robust economic intuition that we have had or that we have held based on our theory. And doing so, imposing this economic structure in this matrix will allow us to recover the structural shocks and the structural parameters using a normal reduced form VAR estimation. So we're going from essentially a structural model, imposing the restrictions, and then converting it in some way to go back to the reduced form VAR and then run it as a reduced form VAR. So essentially, that alleviates this endogenous policy reaction problem that we encountered if we just used a normal unrestricted VAR without any restrictions, right? Therefore, the SVAR identification process is essentially imposing restrictions on matrix A based on some held economic theory to recover the structural shocks and parameters using the reduced form VAR, right? So how do we impose these restrictions? Okay, the minimum number of restrictions required is the difference between the number of unknown and known elements. So for example, let n be the number of variables in a VAR. Okay, let's start with the unknown elements. Well, the unknown elements are the off-diagonal elements of A. So it's like, if this is matrix A is always a square matrix. So these are the off-diagonal elements, and these are like the diagonal elements that you have. Okay, those are the off-diagonal elements. Okay, and by default, right, the all the diagonal elements are equal to unity, right? Therefore, okay, these off-diagonal elements in number are just n squared minus n, okay? Which means that our matrix of contemporaneous correlations, A, has n squared minus n unknown elements, right? Because we know that diagonal by convention will be set to 1 by our construction, then the rest is unknown, that's n squared minus n, okay? So we also know that there are n unknown variances, 1 for each epsilon, and the total of which is n squared, okay, depending on how many things we have. So there are also n unknown variances of epsilon, the total of which is n squared, right? So how do we do this? The known elements now look like this. The estimation allows us to get n squared plus n divided by 2 distinct elements contained in the symmetric variance-covariance matrix of errors, which is this matrix here, which I'll denote as sigma u. The known elements are n squared plus n divided by 2 because for one, we have n distinct elements, 1 for each variable in the VAR. From the diagonal, that's all those ones, right? Those are known, plus n squared minus n divided by 2 elements of the off diagonal. Therefore, the total number of known elements is n squared plus n divided by 2, right? So that's what we get. So to be able to solve the system, we need to impose restrictions, right? Now, why do we need to do this? Because we need to have at least as much equations as we do unknowns, right? So restrictions are based on economic theory and they apply to the contemporaneous correlation matrix A. We would need to impose n squared minus n divided by 2 number of restrictions in order for this system to be solvable. So for example, say we have a VAR with 2 variables, okay? What we would need to do is we would need to impose at least 1 restriction in the in matrix A to be solvable, right? So why is that the case? Well, if you recall, we have n squared minus n divided by 2, okay? If we have 2 variables, so that's 4 minus 2 divided by 2, 2 over 2 is equal to 1, right? So which means that we need to impose at least 1 restriction, okay, in order for our system to be solvable. So that's the computation. Okay, as I mentioned, what we're going to do is we're going to impose that restriction, okay, in the structural VAR. Then we're going to flip it around and run it as a reduced form VAR to estimate, right? So the SVAR is just purely the identification of that exogenous shock. In the process of identification, we need to explore the characteristics of this so-called structural model. Now, suppose we have a structural VAR with 1 lag, say that's an SVAR1. So we have this. Okay, in the structural form, okay, this A is again the matrix of contemporaneous coefficients or correlations, A. Then we have our normal B1, okay, which is a typical coefficient matrix, and then epsilon T. These are the important structural shocks. Okay, so the big idea here is what we want to do is impose restrictions on A in order for us to be able to get the epsilon, which are the structural shocks. And the way we get epsilon is we basically have a formula wherein we can run it, wherein we can convert the SVR to reduce from VR and solve for those epsilons, right? So how do we do that? Say we have 2 variables in our system, namely the output gap, YT, and the real interest rate. So it's an SVR with 2 variables. We then constitute the equation of the SVAR as follows. So we have, okay, these 2 equations. So we have YT for output gap. Okay, so this is output gap. Okay, gap. Okay, and again, the diagonal elements of that matrix are 1. That's why we have that one there, right? It corresponds to itself. Of course, its coefficient, its correlation with itself is 1. It's perfect, right? And then you have these, right? So matrix A is essentially 1, A1, 2, A2, 1, 1, right? And then we have beta naught, which is beta 1, 0, beta 2, 0, right? And then we have beta, okay, which is beta 1, 1, beta 1, 2, beta 2, 1, beta 2, 2. And then we have epsilon, which is epsilon YT, epsilon RT. So if we converge it together, it's going to be AYT, right? And wherein our YT is output gap and the interest rate. Whoops. Output gap and the interest rate equal to beta naught plus beta YT minus 1 plus epsilon. Okay. So that's what we get, right? So that's how it looks like. And in matrix form, it looks like this. That's what we refer to as A. Okay, again, there we go. Now, as I mentioned, we need to impose, if it's a two-variable system, n squared plus n divided by 2, this tells you the number of restrictions you need. We have two variables in the system, so we need one restriction, right? And where do we impose that restriction? In matrix A. That's why matrix A is crucial in the identification. So what do we have? Well, in this example, notice that it has ones in the principal diagonal, while the off-diagonal elements represents the contemporaneous correlations between the endogenous variables. So you have 1, okay, 1, 1, A here, A1, 2, A2, 1. Okay, so those are the contemporaneous correlations. The big idea is, well, we can't really do anything with the 1, okay, but we can do something with these. If we can set these things, say to a particular value, then it's one less thing to solve for, right? And that's a restriction. And maybe that restriction could be based on some economic theory, right? So the elements in matrix A, again, represent the contemporaneous correlations between output gap and the real interest rate. So, okay, now let's get into linking now the SVAR to reduced form VAR. Again, the SVAR is AYT is equal to beta naught plus beta YT minus 1 plus epsilon T. Okay. What we can do is we can pre-multiply the equation by A inverse, right? So we get A inverse YT equal to A inverse beta naught plus A inverse beta YT minus 1 plus A inverse epsilon T, right? So pre-multiplying this equation by A negative 1 will yield us the following, right? So that's what we're going to get, right? That's what I wrote down. And basically, this is going to become, okay, our reduced form VAR, right? Or our unrestricted VAR. So just through one step, which is pre-multiplying by A inverse, we can go from the reduced form VAR to the structural VAR. Now, obviously, we can get what this is, okay? And getting what this is basically through this transformation through A inverse allows us to get what this is, right? So remember, the thing that we want in a structural VAR is to be able to identify those structural shocks. So the key is when we run a normal reduced form VAR that allows us to get U, okay? Then what we can do is we can go from U and then multiply it in some way by A inverse, and we can get epsilon, which is our structural shock. Then we can impose and derive the IRFs, right? So the matrix A also relates the forecast errors, this is what I was just saying, of the reduced form VAR, which is UT, to the structural shocks epsilon T, right? So we know that UT is equal to this. Now, the forecast errors of U are linear combinations of the structural shocks. And in our two-variable example, we can derive this as this case, right? So it's just because A is just equal to 1, A1, 2, A2, 1, 1. And then you can get the A inverse after this one. And then you can get and derive those particular forms, right? So we have a formula, okay, for U, which means that we can isolate out this and this, okay, and we can solve for it, right? We can solve for these things, okay? Now, for example, let's now go into doing what a structural shock will do, right? Suppose there was a surprise growth in GDP, right? There was a surprise in GDP growth. Now, several structural shocks all combined could be affecting GDP, right? There are many things that could affect that. But if we can isolate specifically a certain shock, right? Then it would be brilliant, right? So in the world of shocks, there could be monetary, fiscal elements playing a role in the surprise affecting GDP. And what we need to do is we need to try to distinguish those factors by getting the structural model. Okay, so however, this is not perfect, right? There are caveats to this. Okay, the structural VAR cannot be estimated directly, right? Because you need to impose restrictions. And the structural VAR, as I mentioned before, it's a theoretical construct because you have to impose theoretical restrictions. It's not generally observable. It's just the interpretation of economically, historically available data. Right? So what we believe to be true, we impose it in the structural VAR and we run the VAR as is, right? So when we use these in a VAR, we run regressions of each variable against its past and present values, past values, its own past and past values of other variables in the VAR, and we get our reduced form coefficients, which is A, not script A, and the forecast errors, right? So we can run, and that's what we get. Then we can essentially what we need to do is start with the reduced form VAR and use the matrix A, that script A, the matrix of contemporaneous correlations, to get the structural VAR, right? So run this one first. Then you're going to be able to get this one, right? So the structural form isolates the exogenous shocks and measures the impact of these shocks on the variables included in the model, right? So to do this, we need to get matrix A. To get this matrix, we need to multiply the reduced form of VAR by this matrix in order for us to get the structural model, shocks and contemporaneous relations among other variables, right? So knowing matrix A allows me to go from reduced form VAR to the structural VAR. So we can go through back and then the other way, right? So multiplying A to the reduced form VAR will yield us basically the structural VAR, right? Simplifying, we just get the structural VAR. So how do we now impose the restrictions? Well, in solving an SVAR, again, what we do is the first thing we do is we start with a reduced form VAR and end up deriving the structural VAR. Okay, and this involves directly identifying matrix A. And the reduced form VAR for our output gap and real interest rate example is a little bit easy, but it's nevertheless very interesting, right? So we can write the equations for a reduced form VAR as follows. So say this is a reduced form VAR, okay? And we can collect those, of course, right? So we have 6 coefficients, right? So we have those coefficients from there, right? So these coefficients, so we have A11, A12, A21, A22. So this represents capital A. Then this one is the intercept, that's beta naught, okay? And then we have 2 forecast errors. So we have 6 parameters here in total, and then 2 errors, okay? 6 coefficients. And then you have the variance of the residuals, right, which you can get, right? So, and the covariance. So these are 9 parameters, and there is 6 coefficient estimates, the 2 variances and the covariance. So we have 6, okay, plus the variances, right? Now, this set of estimators should be familiar to you in a reduced form VAR. Now, to estimate the structural VAR, we need to look at how many parameters we are going to estimate. So recall the structural VAR that we had looks like the following, right? And notice this has 10 things to estimate. You have 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10, right? So you have 10 parameters to estimate, okay? You have you have all of these, right? So 4, 6, 7, 8, and then the variances of each of these, right? Right, for each one. So we have 9 we can get from the reduced form VAR. We have 10 from the structural VAR, right? So again, we have no covariance measure here in the a structural VAR because we assume that the shocks are exogenous, which suggests that the covariance is 0. So there's going to be a problem. We have 9 here, 10 here. We need to find a way in such a way that we can reduce this 10 to 9, which is exactly why we need to impose one restriction. So remember, in a two-variable SVAR, we need to impose at least one restriction. It's because we can estimate 9 things with the reduced form VAR, but our structural VAR needs 10 things to be estimated. Well, we don't have 10 equations in the 10 things to 10 sort of degrees of freedom for, so we need to at least cut it down by 1, right? So that's the reasoning why we need to impose a restriction, right? So the problem is that we have more unknowns than equations to estimate it. The reduced form VAR only gives us 9 equations, but we have 10 things to estimate for. So we need to kill off one of those, right? So as a consequence, we need to impose restrictions to be able to solve the model. So in the case of a two-variable VAR, we mentioned earlier, we need 1 restrictions since we have all 9 parameters that are there, right? So, well, the usual approach to go about this is, well, we impose restrictions on the contemporaneous relations among the endogenous variables of the structural model, okay? And for example, okay, we're going to use economics and economic intuition to do so. So say we're going to impose a restriction. This is our matrix A, if you remember. It's equal to 1, 1, A1, 2, A2, 1. We're going to set, okay, what we're going to do is we're going to claim that A1, 2 is equal to 0. Say that's equal to 0, okay? And that means, so this is the key thing here, okay, we're going to assume that that thing is equal to 0, right? And in setting A1 to equal to 0, we are saying that the output gap cannot affect or is not affected contemporaneously by a shock to the real interest rate RT. So in other words, if there's a shock to the real interest rate RT, the output gap will not change immediately in the same period. So if there's a shock at time t, output gap will not move at time t. Right? That's what we mean by contemporaneous at the same period. Right? So when there's a shock to RT, YT will not respond, right? Immediately, right? At the same period. It will respond through its lags, but not immediately. Okay. So if you see RT is absent in the first equation, so RT doesn't directly affect YT contemporaneously. Hence, a shock on RT only affects YT with a lag, right? On the other equation, RT is contemporaneously affected by shocks from YT and, of course, RT. So it means that if there's a shock to output gap, it will impact RT contemporaneously, right? So that makes sense, right? So we have that. So this is now our first equation. We lose the A1, 2 part because, again, that's going to be equal to 0 and everything else is the same, right? Now we can identify the model because we impose a restriction. We go from 10 to 9. Now we have enough equations for the unknowns. This is an example of an exactly identified system, right? So we must, however, be aware that by imposing restrictions on A, you indirectly impose restrictions on A minus as well, on A inverse, right? So again, let's look at the reduced form of the structural VAR, right? So if we pre-multiply by A inverse, okay, you can get, if this is our A, right? This was our A, 1, 0, A2, 1, 1. Whoops. So this is our matrix A. If we take its inverse, okay, if it takes its inverse, we get that, right? So this is going to be the negative because, of course, matrix inversion and matrix algebra gets you that. And if we substitute the matrix, we can get this form here. And of course, from here, we can now get the reduced form VAR, right? And we can be able to estimate everything here. So notice that imposing a restriction on the relation between the reduced form residuals or the forecast errors and the structural shocks allows you to move between them, right? So since we set A12 is equal to 0, the forecast errors of YT, which is UYT, is equal to the structural shock itself, right? So that's because this thing here is 0, right? So simplifying, okay, simplifying. So in parallel, the reduced form VAR estimated OLS has the matrix form below, right? So if you notice, Okay, this was a reduced form VAR. Now, when we impose a structure, this is the reduced form VAR. Okay, it looks something like this, right? So basically, we're gonna run this, which we know has a structure to it, as if it were a reduced form VAR, which it is because we can go from SVAR to VAR, right? How can we do that? We pre-multiply by this script A inverse, and it allows us to get this. But notice that the things inside have changed, right? Because everything is scaled by what we initially put in this matrix A, right? So using the coefficients A, which you obtain with the reduced form VAR, we can build all equations that allows us to estimate and solve for the structural parameters. So we can have all of those, right? All of those are held. Now with the restriction, the number of unknown parameters in the structural model is equal to the number of equations known from the estimated VAR, right? And when we substituted the results from the estimations for the 9 parameters, okay, that we estimated, well, the reduced form VAR will allow us effectively to solve for the structural parameters, which are shown before. And the structural shocks could be recovered, okay, because we impose that the structural shocks to YT are equal to the forecast error of YT, simply because we set A1 to equal to 0, right? And that was caused by the restriction. Okay, now we're going to go into the impulse response functions. Okay, so the impulse response function will trace out the dynamic effects of the structural shocks on the endogenous variables. Okay, and this is the key result that we want from an SVAR. And in each response, okay, each response includes the effect of a specific shock on one of the variables in the system at an impact time t and subsequent periods after that, t+1, t+2, and so on, okay? Building on the responses of the variables to structural shocks requires the model to already be identified with at least some of the structural parameters known. Okay, so to do this, it requires that the SVAR be transformed into a sum of the shocks, okay, which we highlighted in Wolt's decomposition representation, right? So how is this done? Well, that's an IRF, right? So YT can be decomposed as a linear combination of past epsilons, okay? If we have K variables in a system, we should expect a total of K squared impulse responses. So for example, we have a 2-variable system, YT and RT. We should expect a response of YT to YT, YT to RT, RT to YT, and RT to RT, right? So we have 4 IRFs that will be plotted, okay, in the system, okay? Secondly, shocks can be permanent or momentary. If the path laid out in the IRFs is increasing or decreasing as T increases or the horizon moves further, then it's a chance that we have a permanent shock. Although this is quite rare because in economics, we generally expect things to go back to its steady state, okay? So these are examples of the IRFs, right? So this thing here is like a steady state. So here it goes up, then it goes down. So this is if the policy rate goes up, inflation will go up, but will settle down. In here, if if the policy rate goes up, then industrial production will go up and then go down very quickly, and so on. So those are how to interpret impulse responses. And the converse of that, which you can just use a manipulation of, is the forecast error variance decomposition. And it will just tell you, okay, again, we estimate the forecast errors from the reduced form VAR, and it's useful to analyze the relationships among these different variables, right? So in a sequence of movements of the variable, the variance decomposition will give you how much, okay, or what is the proportion of these movements to the shocks itself and to the shocks of other variables. So I think this is easier gotten with an example, right? So in general, of course, we expect that a series' own shocks will explain majority of the forecast error in that variable. So this is an example. So for example here, okay, in this particular case, so for say let's do industrial production. Majority of the share, that's this light blue, is by industrial production, but some of it can be explained by, say, the RRP. Some of the forecast error can be explained by other things there. In here, for example, the RRP, majority is explained by RRP, but some things here can be explained by the CPI and so on. So that's the forecast error variance decomposition, right? So lastly, in the structural VAR is this notion of Granger causality. And the Granger causality is just an application to whether, okay, does the changes in one variable affect the forecastability, okay, not really causality in quotation, the forecastability of another variable. We'll go into Granger causality in the next video. So thank you for your attention. I know it was a long video, but thanks for your attention, and I'll see you in the next video. Thank you very much.